Picture the very first instant of time, the Big Bang. A point of unimaginable energy erupts, creating everything. Energy transforms into matter, following Einstein's EMC2. But there's a cosmic rule. For every particle of matter, an antimatter twin is born. They're mirror images. Same mass, opposite charge. For every electron, a positron. For every proton, an antiproton. This perfect symmetry is written into the fabric of the cosmos. But matter and antimatter don't coexist. They annihilate each other in a flash of energy, leaving only photons behind. In a perfectly symmetrical universe, all matter and antimatter would vanish in less than a second, leaving only a sea of light. No atoms, no stars, no galaxies, no life. The universe would be a silent, sterile void, yet here we are. The Earth, the Sun, the Milky Way, all made of matter. The cosmos is a tapestry of structure and complexity, not an empty void. This undeniable fact presents a profound mystery. If the laws of physics demand perfect symmetry, why is there something instead of nothing? Our very existence is a paradox. The universe should have been empty, but it isn't. Matter survived, and we're here to ask, why? This is one of the greatest mysteries in science. What tipped the cosmic scales in favor of matter? Why didn't everything just vanish? The answer lies at the heart of the universe's biggest contradiction, and it's a puzzle that has driven physicists for decades. Let's return to the first moments after the Big Bang. The universe is a hot, dense soup of particles and antiparticles, constantly created and annihilated. Physics tells us this process should be perfectly balanced, no favorites, just symmetry. We've tested this in particle accelerators. Energy always creates matter and antimatter in equal amounts, yet the universe is dominated by matter. We've searched for antimatter galaxies and found none. If matter and antimatter were equally abundant, their collisions would light up the cosmos with gamma rays, but we see no such signals. Antimatter is rare, fleeting, and only appears in high-energy events or labs. The Standard Model insists on symmetry, but the universe disagrees. Something broke the balance, allowing a tiny fraction of matter to survive. The universe as we know it is the debris from a cosmic war that matter won. Without that victory, we wouldn't exist. Our experiments confirm symmetry, but reality shows a clear bias. What intervened in those first moments to tip the scales? The answer remains one of the deepest puzzles in physics, and it's the reason we're here to ask the question. How did matter win? The leading idea, a tiny imbalance. For every billion pairs of matter and antimatter, there was one extra particle of matter. After the annihilation, that lone survivor became the seed for everything. This billion+1 hypothesis explains why there's something instead of nothing. The annihilation's energy became the cosmic microwave background, the afterglow of the Big Bang. For every matter particle, there are about 1 billion photons in the universe. This ratio tells us the original imbalance was minuscule, 1 part in 1 billion. The challenge: what caused this tiny, crucial asymmetry? What subtle flaw in nature allowed matter to win? Physicists are still searching for the answer. But that tiny excess is why we exist. In 1967, physicist Andrei Sakharov outlined 3 conditions for a matter-filled universe. First, the universe must allow processes that violate baryon number conservation, meaning the number of matter particles can change. Second, the laws of physics must break certain symmetries, specifically C symmetry and CP symmetry, so nature can distinguish matter from antimatter. Third, these processes must happen out of thermal equilibrium, during rapid cosmic change. Without all 3, the universe would be empty. Sakharov's recipe became the foundation for theories explaining why matter survived. These conditions are the keys to our existence. But how did the universe actually meet them? Physicists call the creation of matter baryogenesis. Grand unified theories, GUTS, propose that, in the early universe, super-heavy particles decayed in ways that violated Sakharov's conditions, creating a matter excess. Another idea, leptogenesis, suggests heavy neutrinos decayed asymmetrically, producing more leptons than antileptons. Rare processes then converted this lepton imbalance into a baryon imbalance, turning an excess of electrons into an excess of protons and neutrons. Leptogenesis also helps explain why neutrinos have mass. Both theories hinge on subtle violations of symmetry and rapid cosmic change. The details are complex, but the goal is simple. Explain why matter survived. The search continues for evidence of these early universe processes. Sakharov's second condition, CP symmetry violation, has been observed. In 1964, physicists discovered that certain particles and their antiparticles decay differently. This proved nature can distinguish matter from antimatter, but the amount of CP violation we found is far too small to explain the universe's matter. The Standard Model can't account for the imbalance we see. There must be a larger, hidden source of CP violation. This suggests new physics beyond our current theories. The fact that we exist is evidence that the Standard Model is incomplete. The answer lies in undiscovered realms of the cosmos. The missing antimatter pushes us to imagine new physics beyond the Standard Model. Grand unified theories and supersymmetry offer possible answers. Supersymmetry proposes new particles and interactions that could provide the extra CP violation needed. Some supersymmetric particles could also be dark matter, solving two cosmic mysteries at once. Our universe appears fine-tuned for our existence, a slight change, and we wouldn't be here. The missing antimatter is a clue pointing to deeper truths. The universe we see is just one chapter in a grander story. The most exciting discoveries still await us in the dark.